Definition: a random process represents scenarios where the outcome of any particular trial of an experiment is unknown, but the proportion or relative frequency of a particular outcome is observed approaches a specific value as the number of trials increases. What does that mean? So I know that when I flip a coin, half the time it should land on heads and half the time it should land on tails, right? So the probability of landing on heads should be 1/2. But if I flip a coin right now, if I were to flip a coin right now, I don't really know which one it's going to land on, right? So for a given instant, the outcome's random. I can't tell you if it's going to land on heads or tails on a particular flip. But what I can tell you is if I flip the coin a bunch of times, half of the time it's going to land on heads and half of the time it's going to land on tails. That's the idea that we're getting at with this random process. So a particular trial is a term there that we're going to have to define, but a trial would just be like a given flip of the coin. So for a particular trial, I can't tell you what's going to happen, but I can tell you what's going to happen if I repeat the trial a bunch of times. Probability is a measure of the likelihood of a random phenomenon or chance behavior occurring. Probability deals with experiments that yield random short-term results or outcomes, yet reveal long-term predictability. The long-term proportion in which a certain outcome is observed is the probability of that outcome. So again, if I flip a coin, say 1,000 times, I'm going to get around 500 heads and around 500 tails. So 500 out of 1,000, that's a half. In the long run, the probability is going to be the result of repeating the outcome over and over and over again. So in the short term, I can't tell you for sure what proportion of heads I would get, but in the long term, I can. What I'm getting at is called the law of large numbers. As the number of repetitions of a probability experiment increases, the proportion with which a certain outcome is observed gets closer to the probability of the outcome. So if I were to flip a coin 4 times, I might get heads all 4 times, which would be 100% heads. So in the short term, I might get a proportion that is not anywhere close to the true probability. But if I continue to flip that coin, as I said earlier, 1,000 times, then if it's a fair coin, I am going to get about 500 heads and about 500 tails. The law of large numbers, the proportion of heads is going to approach the true probability. Now, I may not get exactly 500 heads. I might get 497 heads, but I'm not going to get 200 heads if it's a fair coin. I mean, it's not impossible, but it's very, very, very unlikely. I am going to get close to 500 heads. So example, suppose a coin is flipped 100 times and the proportion of heads observed after each toss is computed. Figures A and B below show 2 repetitions of this experiment. In both cases, the proportion of heads approaches 0.5, which is the true probability as the number of flips increases. So we just have 2 examples of flipping a coin 100 times. And what we're keeping track of in this graph is the proportion of heads. So when the first coin was flipped, it landed on tails. And so that meant there was 0% heads at that time. When I flipped the coin the second time, it landed on heads. So now I had the first one was tails, the second one was heads. So that's 1 out of 2, or 50% was heads. So we're here at 0.5. On the third flip, it landed on heads again. So now I have 2 out of 3 that are heads. So the proportion is 2/3. I flip the coin a 4th time, it lands on tails. So now I'm back at 50%, 2 heads out of 4 flips, back at 50%, and so on. So it's tracking the proportion of heads at any given number of flips. Now again, it's random, So this actually stayed above a half for a long time, but as we keep repeating, it stayed above a half for a long time, but then the more we go, the more it goes towards the true probability, 0.5. This is just doing the same thing. On this one, we landed on heads on the first flip, so it was 100%. We landed on heads on the second flip, so still 100%, 2 out of 2. The third flip was a tails, so now we're at 2 out of 3, so we drop down here. And then next we hit tails again, so now we're at 50%, 2 out of 4, and so on. Now this time it kind of hovered around a half, and then it went above a half, then it went below a half, and above a half, and it's kind of settling around the half. So again, this is illustrating the law of large numbers. Whatever the probability is, if you keep repeating an experiment for that probability a large number of times, you're going to approach the true probability. The law of large numbers is how industries such as casinos are guaranteed profit. Casinos know the probability of you, the gambler, winning or losing a game. And they structure their bets in a way that they have a slight advantage. You might have a streak. Let's say you're at the craps table or something like that. You might have a streak where you are avoiding crapping out, so to speak. But eventually you will crap out. So you may have a long winning streak, but if you keep playing, the longer you play, the more likely it is that you're going to approach the true probability. And as you approach the true probability, it's to their advantage. So my advice is, if you go to the casino and you get ahead in craps or blackjack or any game of your choice, the best advice I could give you is when you get ahead, quit. Because otherwise you will eventually lose the more you play. So the best strategy, play, get ahead. If you get ahead, quit. So in probability, an experiment is any process with uncertain results that can be repeated. So we've used the term experiment previously, but now we're going to use it a little bit differently. We're talking about a probability experiment. In a probability experiment, we're not talking about the same kind of thing when we talked about designing an experiment back in chapter 1. So we're not manipulating the variables really. A probability experiment is just some process that has an uncertain outcome, like flipping a coin. And it has to be able to be repeated. So I could flip a coin repeatedly. Rolling dice, the outcome's uncertain, and I can repeat the process. So rolling the dice can be a probability experiment, and so on. Each time we repeat the process, that's called a trial. So my first flip is a trial. My second flip is a trial. My third flip's a trial, and so on, of the probability experiment. Or if my first roll of the dice, that's a trial. My second roll of the dice, that's a trial, and so on. So that's what this is talking about up here when it uses the word trial and experiment. So we're talking about a process with an uncertain outcome, and we can repeat that process. And so each repetition is a trial. Definition. The sample space S of a probability experiment is the collection of all possible outcomes. An event is any collection of outcomes from a probability experiment. An event consists of one outcome or more than one outcome. We will denote events with one outcome, which are called simple events, by a lowercase letter such as E with a subscripted number. So like E sub 1 would be simple event 1, or the first outcome, so to speak. E sub 2 would be simple event 2, the second outcome, and so on. In general, the events are denoted with capital letters such as uppercase E or uppercase F or uppercase G or something like that. So the difference between an uppercase E is that this could represent multiple outcomes, whereas a lowercase represents a single outcome, again called a simple event. So sample space, if I'm talking about flipping a coin, my sample space, which is going to be denoted by capital S usually, flipping a coin would be heads, tails. That's it. I've listed all the possible outcomes when I flip a coin. It either lands on heads or it lands on tails. So the sample space is that list or that set of possible outcomes. So I might have simple event 1 might mean that I get heads. Simple event 2 might be that I get tails. Example, suppose a coin is flipped twice. What is the sample space? So now I'm not going to just flip a coin once, I'm going to flip a coin twice. So I'm going to flip it, and then I'm going to flip it again. What are the possible outcomes? What is the sample space? Well, I could possibly get heads on the first flip, and then I could get heads again on the second flip. That is one possible outcome. I could possibly get heads on the first flip and tails on the second flip. I could possibly get tails on the first flip and heads on the second flip. Or I could possibly get tails on the first flip and tails on the second flip. These are the only 4 possibilities. So I could get heads, 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 tails, tails, heads, or tails, tails. That's it. Those are the possibilities. So this might be event 1, event 2, event 3, event 4. So these would be simple events. Whereas if I just said, what's the probability of getting at least 1 tails? At least 1 tails would mean it could be this, this, or this. So if event E is getting at least 1 tails, then that would consist of HT, TH, or TT. So this isn't a simple event because getting at least 1 tails could be any one of these 3 things. So sample space is all the possibilities. The event is whichever possibilities meet whatever the question's asking about. So in this case, at least 1 tails. These are the outcomes that have at least 1 tails. B, suppose a coin is flipped 3 times. What is the sample space if I flip the coin 3 times? Well, the more flips, the harder it gets to list all of the possible outcomes. I could possibly get heads on the first flip, and then I could possibly get heads again on the second flip, and then I could possibly get heads again on the third flip. Or I could get heads on the first flip, heads again on the second flip, but this time get tails on the third flip. That's a different outcome. Now, those are the only 2 outcomes where I get heads on the first flip and heads on the second flip. Now, I could get heads on the first flip and tails on the second flip. So if I get heads on the first flip and tails on the second flip, then I could possibly get heads on the third flip. Or if I get heads on the first flip and tails on the second flip, I could possibly get tails on the third flip. So these are the only 2 outcomes where I have heads on the first flip and tails on the second flip. Again, if it's heads, tails, then I could either have heads on the third flip or tails on the third flip. Those are the only 2 possibilities. Now, incidentally, these 4 outcomes are the only 4 outcomes possible if I get heads on the first flip. So if I get heads on the first flip, it's got to be one of these 4 things. What if I get tails on the first flip? If I get tails on the first flip, I could possibly get heads on the second flip and heads on the third flip. Or if I get tails on the first flip, I could possibly get heads on the second flip and tails on the third flip. So these are the only 2 possibilities if I get tails on the first flip and heads on the second flip. I could also get tails on the first flip and tails on the second flip. If I get that, then I could either get heads on the third flip or I could get tails on the third flip. So these are the only 2 possibilities if I get tails on the first 2 flips. And these 4 outcomes are the outcomes if tails is the first flip. If I get tails on the first flip, then I could get this, 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 this. Those are the only 4 possibilities. So altogether, there are 8 possible outcomes when I flip a coin 3 times. So this is the sample space. So again, this could be a simple event 1, simple event 2, simple event 3, simple event 4, 5, 6, 7, 8. Or I could ask a more general question that needs a larger event. Like I may again say, what's the event of getting at least 2 tails? Well, at least 2 tails could be this, or this, or this, or this. So the event of getting at least 2 tails would be heads, tails, 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 heads, tails, 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 heads, or tails, tails, tails. Or I might ask, list the event of getting exactly 2 tails. Exactly 2 tails would consist of this, this, and this, but not this because that's more than 2. So exactly would be these 3. The trick to probability is making sure you find what you're asked for. So probability as a concept is not hard. You already understand probability. What's difficult about probability is that it's tricky. You have to be very precise. So when you're asked to find like the event of exactly 2 tails versus at least 2 tails, you got to pay attention to the words, right? So at least means it could be 2 tails or more. Exactly means it has to be 2 tails. So you got to pay attention to those kinds of things. Probability rules. Now we're going to have a lot of probability rules, but there's 2 sort of basic ones that we start with. The first probability rule is that a probability has to be between 0 and 1 inclusive. So a probability could be 0, a probability could be 1, or a probability could be anything between 0 and 1, but it cannot be anything outside of the range between 0 and 1. So there's no such thing as a negative probability. So you can't have a probability of -1/2. And there's no such thing as a probability greater than 1. So there's no such thing as a probability of 1.2. Doesn't exist. Probability is always going to be a value between 0 and 1. So the probability of any event E, which we're going to denote by P of E. So that's like function notation. P for probability, E's inside the parentheses, so it's the probability of event E, whatever event E is. Must be greater than or equal to 0 and less than or equal to 1. That is, 0 is less than or equal to P of E, which is less than or equal to 1. So again, probabilities have to be something between 0 and 1. It can be 0, it can be 1, but it can't be beyond that. The second rule, the sum of the probabilities of all outcomes must equal 1. That is, if the sample space S equals event 1, event 2, and so on, and these are simple events up through E sub n, then the probability of simple event 1 plus the probability of simple event 2 and so on plus the probability of simple event n has to add up to 1. Add all the probabilities up, they got to equal 1. A probability model lists the possible outcomes of a probability experiment and each outcome's probability. A probability model must satisfy rules 1 and 2 of the rules of probabilities. So it must follow both of these rules. So an example, the color of a plain M&M milk chocolate candy can be brown, yellow, red, blue, orange, or green. Those are the only 6 options on a standard plain M&M. So I'm saying standard, so we're not talking about like the special holiday packages or anything like that. And we are talking about plain M&Ms, so just the chocolate inside. We're not talking about peanut M&Ms or almond M&Ms or Rice Krispies M&Ms or any of that kind of stuff, right? They got all those other ones now. They have different results. But for a plain M&M, you can have brown, yellow, red, blue, orange, or green. Suppose a candy is randomly selected from a bag of M&Ms. The table to the right shows each color and the probability of drawing the color. And this information comes from the company, M&M Mars. So according to them, the probability of drawing out a brown M&M is 0.13. In other words, 13% of plain M&Ms are brown. The probability of drawing out a yellow M&M is 0.14. In other words, 14% of plain M&Ms are yellow. Red, 0.13, blue, 0.24, orange, 0.20, green, 0.16. Verify that this is a probability model. That should be a period, not a comma. So verify this is a probability model. So we have each of the 6 outcomes. That's the first thing. You got to list all of the possible outcomes, and you have to have the probability for each one of those outcomes. The rules have to be followed up here. So each one of these probabilities has to be something between 0 and 1. Could be 0, could be 1, or anything in between. So there are no negatives here. There are nothing that is bigger than 1. So these are all valid probabilities. Now, the last thing is, if we add them all up, the result has to equal 1. So if I bring in my calculator here, if I add up 0.13 plus 0.14 plus 0.13 plus 0.24 plus 0.20 plus 0.16, that adds up to 1. So if I add that up, that adds up to 1. So this is a probability model. Notation-wise, I will usually indicate this right here. That is the sum of P of X. I'm adding up the probabilities, and it adds up to 1. So how about this? Which of the following could be a probability model and which could not? Explain why. So I have the same kind of deal. We're talking about colors of candies or something. And we have different values over here. Could this be a probability model? What I'm looking for is, are each of these valid probabilities? Can a probability be 0.3? Yes. 0.15? Yes. 0? Can a probability be 0? Yes. 0.15? Yes. 0.2? Yes. 0.2? Yes. So all of these are valid probabilities. So the only other thing I really need to check is, does that add up to 1? So if I bring in my calculator, 0.3 plus 0.15 plus 0 plus 0.15 plus 0.2 plus 0.2, that does add up to 1. So this can be a probability model. So I'm going to just write yes. Yes, this could be a probability model. Could this be a probability model? I'm going to check the same things. That's valid, 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 valid. All of these are between 0 and 1, so all of those are valid probabilities. If I add up 0.1 plus 0.1 plus 0.1 plus 0.4 plus 0.2 plus 0.3, that adds up to 1.2. That does not add up to 1. So this cannot be, it cannot be a probability model because it doesn't meet the condition that these probabilities add up to 1. What about this? Could this be a probability model? So everything's from 0 to 1, so these are all possible, and if you add it up, it adds up to 1, so yes. Now this is a kind of a boring probability model. If we're talking about plain M&Ms, this would be like a bowl that has all yellow M&Ms in it. So it's not possible to draw out a red, a green, a blue, a brown, or orange because all the M&Ms are yellow. But that is a possibility. This is valid. What about this one? What's wrong? You can't have a negative 0.3 probability.